Hello, and welcome back to Sounds of Heaven. In today's video, we're going to dive deeper into one of the most fascinating topics in physics, space-time. Now, I know this sounds a bit complex, but stick with me, and I'll try to explain it in simple terms. Let's start at the very beginning. What is space-time? Well, as the name suggests, it refers to the fusion of the three dimensions of space and the one dimension of time into a single, four-dimensional structure. Before Einstein came with his theory of relativity in the early 1900s, space and time were thought to be completely separate entities. Space was just a three-dimensional arena in which matter exists and events take place, while time was its own independent thing that ticked steadily away. However, Einstein showed that space and time are actually intimately linked, and different observers can disagree on measurements of space and time depending on their speed of motion.
So if we think of space the traditional way that the ancient Greeks and Euclid did, it was just a boring stage on which events unfolded over time, right? Whereas what Einstein said in his first special theory of relativity is that you shouldn't think of all these frames one by one as something happening, but you should think of space-time as just the whole videotape. That's how I think of space-time. And the whole story is just in there. And then his second theory, the general theory of relativity, he came up with this even more radical notion that, moreover, space isn't just static, this backdrop on which other things happen, like the electric field moves around and stuff, but space-time is actually a mover and a shaker, in the sense that space can shake. You can have these ripples called gravitational waves, which are just ripples in the fabric of space-time itself. The space can move away from other parts of space in a stretchy, which is what we mean when we say the universe is expanding, and space can curve a little bit, where the curvature turns out to correspond to stuff, matter, and a lot corresponding to black holes. And maybe space can even melt, which is the latest business for the whole string theory landscape. So in other words, I think we've completely transformed our view of space-time as just being the boring, static backdrop to being a very active participant in the universe.
So, space-time is the unified fabric of the universe that contains all events and things. We obviously can't visually picture a four-dimensional structure, but we can conceptualize it mathematically. Now, what is the fabric of space-time actually made of? Well, as far as we know, it's not actually made of any substance. It is the mathematical model we use to understand the relationship between space and time. However, a distinction has to be made so as to not confuse two different concepts. In a 2021 study by Agrawal entitled Structure of Space Fabric, a distinction was made between space-time and the fabric of space, which, according to Agrawal, is composed of dark matter, dark energy, and so on. For the purposes of this video, the fabric we talk about here is the three dimensions of space and the one dimension of time. You can kind of imagine it like a stretched out, flexible sheet that can bend and curve in response to matter and energy. The presence of mass causes dents and warps in the fabric, and these warps are actually what we perceive as gravity. The heavier the object, the more it distorts the surrounding space-time. However, this is a concept that is only visualized in two dimensions. In order to view it in the three dimensions we can see, it will look like something like this. So, instead of thinking that an object's mass bends space-time downward, you can visualize it as bending on all sides. Now, to get more perspective on that, let's talk about Einstein's theories of relativity and how they relate to space-time. His theory of special relativity deals with observers moving at constant speeds relative to each other. It showed that time passes slower and objects shrink in the direction of motion of someone moving very fast relative to someone who is stationary.
Our perception of time depends on how we are moving. So if you are just sitting still and I'm traveling at some constant velocity relative to you, my perception of time will be different than yours. And this looks strange, it looks counterintuitive, but this is the way the world works. And so you can take two clocks, two identical clocks, and then move them relative to each other, and they will measure different times. So it's a fundamental way about how things work. So this is very dramatic for particles that are moving very fast. So if a particle that lives at rest lives for, I don't know, 1 second, if you move it very, very fast, it lives for much longer. So it's a dramatic effect for particles that are moving very fast.
His later theory, the theory of general relativity, deals with accelerated motion and gravity. It proposes that what we feel as gravity is the effect of objects warping and distorting the fabric of space-time. For example, the sun's huge mass warps and distorts the surrounding space-time, and Earth moves around the sun because it is caught in this dent, like a marble rolling around a bowling ball sitting on a trampoline.
According to Einstein, if you go and have a star, that star will bend space-time in that extra dimension that you can't see. See, you can't see it bent up over there, but you can see it here. And that bent space-time, if you roll the ball, see now it looks like it's going around and around that planet. So according to Einstein, there is no connection between the star and the planet. What you have is the star bending the fabric of space. And this little fabric pulls on that, which pulls on that, which pulls on that, which pulls on that. There is no action at a distance. There's only this pulling on the stuff right next to it. And then when the ball goes around and around, it's because of that curvature going around. If you have a heavier star, a more massive star, it's going to curve space-time even more. So watch this. It really looks like a planet going around a star.
Relativity thus showed us that space and time are flexible and fundamentally connected.
I think one of the most important ideas is the idea that space-time is not a static concept. It's not some background where particles move. It's not a stage where actors move, like the particles are the actors that are talking and the stage is fixed. The stage is not fixed. The actors modify the stage. And so space-time is modified by particles. So when you have a heavy particle, it curves space-time. So space-time can be curved. If you shake a particle, it will emit a wave of space-time. But, well, this theory of general relativity is called, it's a theory of gravity. It's also tested in many situations, and we believe it's basically right.
To give you a sense of scales, as an extreme example, at the event horizon of a black hole, which we'll talk about in the next video, the space-time distortion is so great that it forms a bottomless pit, from which not even light, with its incredible speed, can escape. Overall, the effects of relativity are only noticeable with high speeds, large masses, or strong gravity. Under ordinary conditions here on Earth, we don't observe any weird time dilation or length contraction effects, so space-time appears to be stable and universal in our day-to-day lives. Now, why is the concept of space-time so important? Well, it overturned the classical notions of absolute space and time to show that they are relative. This revelation has required developing a whole new physics to understand the cosmos. It provides the framework for understanding principles from time travel to black holes. And the flexibility of space-time poses a profound question. Are space and time fundamental aspects of nature, or do they emerge from an even deeper quantum phenomenon? I hope I have provided you with a helpful basic introduction to get your mind wrapped around this weird yet extremely important concept. Let me know if you have any other questions. In the next episode, we're going to use our understanding of space-time to delve into one of the most mystifying objects in the cosmos, black holes. How does their immense gravity warp space-time so severely that nothing can escape? What happens at their center, inside the event horizon? Stay tuned to find out. If you want more videos like this, please subscribe to the channel so we can continue to provide you with more interesting facts about the cosmos. This was Sounds of Heaven. See you in the next episode.